All right, so let's talk about indexing and performance. How different indexes and whether it's a unique index or non-unique index, and how does it affect performance. So we had mentioned earlier that we were going to consider two different indices on the student table. One was going to be a non-unique index major ID, which was an index on a foreign key, right? And that foreign key, we know definitely is not a unique field, right? It's going to have repetitions quite a bit, right? Because you have multiple students in the same major. Whereas you can have a unique ID index on a foreign key that it is guaranteed to be unique. So let's take a look at how these indices might perform differently, right? So obviously on the unique index, we know that there's a one-to-one relationship between the index that we create for student number 10 that references one single student on the original record. Whereas in the non-unique index, because in this particular case we're using the foreign key, right? If you have a particular value for major ID 10, that could be referencing 10, 20, 100, 1,000 students that are in the same major, in the same college, in the same department. So we like to see how the performance might be affected on whether it is a unique or non-unique index. So let's take a look at this graph. So here's an example on how whether it's unique or non-unique might affect the search and retrieval of these records. So we're going to find a student whose student ID is 8, and from a student table. So we know that student ID is a primary key. We are retrieving the major ID. That doesn't matter. So we want to find the student whose ID is 8. Now we know that if there were no index, right, then and we can't guarantee that it has been sorted or organized in any particular way. And then the only thing that we have left is linear search, right? We're just going to have to iterate record by record until we find the student whose ID is 8. Worst case scenario, this student is at the bottom of the table. We're going to have to iterate over all 40,000 students until we find that one student with student number 8. Best case scenario is the first student, right, in the table, and we find it right away. In general, right, on average, we know that it's going to be somewhere in the middle, right? So we say that on average, it'll take you n over 2 comparisons to find the record that you're looking for if you're using linear search on average. But if we know that it's an index, right, that the table has been indexed, we certainly don't ever have to iterate over all 40,000 students in the university looking for student ID 8, right? Instead, we're not going to use the original table. Instead, we're going to be using the index, right? And we know that the index has been organized, has been sorted, right? So instead of using linear search, right, we can use binary search. Well, binary search, if we're using binary trees, but we already said that our trees are not binary, right? It could be it's much flatter. It's still proportional to a logarithmic of the height of the tree, of the number of elements, right? But the height of the tree is even shorter, even less shorter than the binary tree. But anyway, we can use just a couple of comparisons, to go from the root of this tree all the way down to the record. It might take a couple of comparisons, maybe 5, 10 comparisons to traverse the tree, from the root all the way down. And once we are at the index, we're going to have a record, right, identifier, a field that is going to have a reference to where the original record is, right? So going from that record to the original record, that's easy, right? It's a very quick operation, and then we can retrieve the record right away and give it back, right? So certainly it's not going to be the worst case scenario. We're going to have 40,000 comparisons. It's certainly going to be several orders of magnitude faster than 40,000 comparisons.